presentation today focuses on multi-level construction and compliance. Jason Wanden from Sto will be talking about key compliance areas for render facade systems and how key performance tests completed by Sto can be applied. Jason will take a look at the use of StoPoren Panel Facade systems, incorporating their product StoPoren, aerated concrete panels, specifically on multi-level residential and commercial construction. Jason will be covering considerations of the New Zealand Building Code clauses B1, structure, B2, durability, C3, spread of fire, and E2. Jason, if you haven't met him, he's spent 28 years in the architectural specification and construction industry. He's had over 15 years project management and product evaluation experience with brands. Jason, over that time, has developed skills in product development, testing, consulting, compliance, and quality assurance. And for the last 2.5 years, Jason has been working as part of the technical team at Sto. Jason, good afternoon. How are you?
Yeah, very good. Thanks, Matt. Very good indeed.
Nice, colourful background there. So that's brightening up everyone's day.
It's pretty grey outside.
Thank you for sharing screen. Over to you.
All right. Hey, yep. Thanks again, Matt. Look, welcome everyone. It's my pleasure to be with you today. I was meant to be about 20,000 kilometres away, enjoying the sun in Spain about now. But since COVID put an end to that, what better way to spend an afternoon than talking about facades? So look, we'll get straight into it. Sorry, I'll get back. With a move to higher density housing and inner city apartments, more and more of our buildings are stretching in height, well above the scope limitations of E2AS1. My presentation today will take us through the compliance considerations for facade systems, and in particular, we'll be looking at the use of cavity-based aerated concrete cladding systems. Facade design. The facade of a building plays an important role in contributing to the amenity and attractiveness of an area. Facades should be well considered and designed as an integral part of the building. As I mentioned before, this presentation will be focused on aerated concrete or AAC facade systems. And we'll use the StoPoren Panel Facade system as an example to highlight some of the NZBC compliance requirements and considerations. The graphic in this slide provides an outline of the typical system layers and components of an AAC system. Layer 1 is the building frame and wall underlay. More often than not, the underlay on multi-level construction will be a proprietary rigid air barrier system. It'll play a role not only in the weather tightness performance, but also resisting wind pressures and protecting the structural frame from fire. Layer 2 is the cavity batten, typically 20 millimeters thick. With the need for materials of limited combustibility in the cavity space of multi-level construction, more often than not, this will be a fibre cement, aluminium, or in the case of a tested system, a timber cavity batten. Layer 3 is the aerated concrete panel, in our case, the StoPoren panel. The panel is installed over the cavity battens with structural fixings penetrating through the cavity into the structural wall frame behind. The StoPoren panel is then finished as outlined in layers 4 to 6 with the Stoanz Miral fiberglass mesh reinforced render system with selected finishing renders and facade coatings. As outlined on the previous slide, StoPoren panels are manufactured from autoclaved aerated concrete and they're reinforced with a steel mesh. The panels are 2.2 meters long, 600 millimeters wide, and either 50 or 75 millimeters thick. They are laid horizontally across the cavity battens to provide a solid, permanent substrate for the render system. The mass of a 50 millimeter thick panel is approximately 32 kgs per square meter, which is about 20% that of concrete. The New Zealand Building Code is a performance-based building code. It sets clear expectations of the standards a building should meet. It consists of 38 technical clauses, and within each technical clause, the requirements are explained in 3 levels. There's the objective, which is the social objectives from the Building Act. There are the functional requirements, the functions that the building must perform to meet the objective, and for the performance requirements, which is the performance criteria the building must achieve. And by meeting the performance criteria, the objectives and functional requirement can be achieved. So to summarise, the building code states how a building must perform its intended use rather than describing how the building must be designed and constructed. The key NZBC compliance areas for facades are Clause B1 structure, which requires buildings to withstand the likely loads they'll be subjected to during their serviceable life, including wind and earthquake. Clause B2 durability, which requires the materials used in the construction of the facade to remain functional for the minimum period specified. And in this case, it's 15 years for the panel and render systems and 5 years for the facade coating. Clause C3, fire affecting areas beyond the source, including horizontal and vertical fire spread. And Clause E2, external moisture, which requires the external facade to prevent water from causing undue dampness and damage to the building structure. Clause B1 is about structural failure resulting in injury, loss of amenity as defined by the building regulations, and physical property to other damage, or physical damage to other property, beg your pardon. Physical conditions that need to be addressed for facade cladding include self-weight, which is the system's ability to resist its own weight when installed on the wall, earthquake, and the system's ability to withstand SLS seismic events and remain functional as a cladding, and also ULS seismic events without putting human life at risk. Wind, the system's ability to withstand wind pressures on the facade, and impacts, and that's the system's ability to withstand hard and soft body impacts as appropriate for the building's use. The StoPoren panel system has been subjected to a range of structural tests at brands. This included wind face load to determine the system's resistance to wind suction pressure, racking to determine the system's resistance to damage under seismic deflection, and in-plane shear strength to determine the panel fixing's ability to support the weight of the panel and resist the forces applied by the panel suspended out on the cavity. Assessments were completed for both timber and steel frame construction. The structural performance of the system was also assessed during the facade testing to AS/NZS 4284. The panel was subjected to positive and negative pressures of 4.5 kPa and was also subjected to deflection along the line of the mid-floor before being retested from a weather penetration perspective. Facade systems are typically required to meet the NZBC durability requirements of 15 years for the cavity system and facade panel and 5 years for the paint or coating system. B2.3.2 though is an important consideration as well, as it states that individual components of the building system are required to have the same durability or be installed in a way that enables their replacement without having to remove the building elements that have a greater durability. An example of this is wall underlays, which may only have a 15-year durability requirement in isolation, but are required to have a serviceable life equal to that of the facade cladding that covers it. Testing of StoPoren panels was completed at brands. It included assessments of compressive strength, moisture movement, corrosion protection of reinforcement, which is probably one of the more important assessments to ensure that the steel reinforcing mesh is adequately protected from moisture, and composition analysis to determine the mineral composition and the mineral structure of the aerated concrete. The stow renders and coatings have also been subjected to testing by brands, and that's across multiple systems, not just the StoPoren system. The testing included adhesion to substrates and resistance to UV. An expert opinion confirming compliance of the system with the NZBC performance requirements was provided on the basis of this testing. As the pictures attest, the StoArmat and StoLitK renders are highly flexible and resistant to fracturing and mechanical stress. The StoArmat render has an impact resistance of about 10 times that of cement-based or mineral products. There are two performance clauses that describe the constraints for control of external fire spread. Clause C 3.5 sets the requirements for limiting the vertical fire spread of fire, and Clause C 3.7 covers horizontal fire spread and the ignitability of the wall cladding materials. It should be noted that vertical fire spread considerations only kick in when the building height is greater than 10 metres. Significant high-rise events globally over the last few years have increased the understanding of how fire spreads externally and within modern facade construction. One of the first was the fire at the La Crosse apartment building in Australia. The cause of the blaze was revealed to be an unextinguished cigarette left in a plastic food container on a 6th floor balcony. It spread to the timber tabletop and then to a nearby air conditioning unit. Flames ignited the external wall cladding, and aided by the combustible material located within the wall structure, it quickly spread to the top of the building. This little animation highlights the speed at which the fire was able to spread up the facade, covering levels 6 to 21 in approximately 10 minutes. Probably the most well-known of the recent fire-related disasters is the Grenfell Tower, primarily due to the catastrophic loss of life. The exterior cladding of aluminium composite panel encompassing a combustible core of polyethylene and plastic insulation contributed to the rapid spread of fire in just 1 hour. A couple of these photos, 1:30 in the morning is that first photo. You can see a little over an hour later, the building is well consumed, and sort of 2¼ hours later, there's not much left. As a follow-on from the guidance document released in February 2019, MBIE have recently undertaken consultation for the amendment of the NZBC acceptable solutions and verification methods as they relate to protection from fire. In particular, they are looking to amend the fire testing requirements for cladding systems to reference large-scale international standard tests. A focus on vertical fire spread sees not only the face of the facade, but also the materials within the external wall cladding system needing to be addressed. Consultation is closed, however, the next building code change has been delayed due to COVID until September this year. A key to the prevention of fire spread is the selection of materials within the cladding system that are combustible or of limited combustibility. StoPoren panel has been tested to AS1530 Part 1 and is deemed to be non-combustible. This is great as it means that the exposed face of the panel in the cavity space will not support the vertical spread of fire when coupled with a non-combustible or otherwise verified cavity system. Acceptable heat release rates for external wall cladding systems for the control of horizontal fire spread still remain a requirement, depending on the building height and the distance to the relevant boundary. The StoArmat render system over StoPoren panel has been tested to ISO 5660 Part 1 and achieved the performance level A classification. One of the new definitions likely to be included in the building code update is limited combustible. A material that has limited combustibility is classified as A2 when tested to BS EN 13501 Part 1. These materials contain minor amounts of combustible material, but are unlikely to significantly contribute to the spread of fire. STO renders have all been tested to EN 13501 Part 1 and have achieved A2 classifications. An example of a couple of the international test standards proposed for inclusion in the NZBC update are BS 8414 and AS 5113. Both of these standards require the testing of a full-scale facade with a height of approximately 9 metres and a width of approximately 3 metres across the main face with a 1.5 metre wing wall. The space you can see at the bottom of that panel is filled with 360 kgs of dry timber, which is lit and to propel flame up the face of the facade. The external moisture clause is all about preventing the penetration of water that could cause undue dampness and damage to building elements. There are several weather tightness verification methods that are accepted typically as a means of demonstrating compliance. E2VM1 is designed more as a verification method of claddings for buildings within the scope of E2AS1, so not specifically suited to multi-storey construction. AS/NZS 4284 is a verification method for commercial facade systems. It tests multiple aspects of facade performance, including structural strength and water penetration. E2VM2 is the newest of the verification methods available and represents a series of tests from AS/NZS 4284 for assessing the weather tightness performance of domestic-oriented wall cladding systems for use on buildings between 10 and 25 metres high. The StoPoren Panel Facade system has been tested to AS/NZS 4284 with test pressures based on a design wind pressure of 4.5 kPa ULS. The system was also tested to E2VM1 with standard and elevated pressures aligned with the requirements of E2VM2. The system successfully met the requirements of both those verification methods. So in summary, STO's undertaken a series of independent verification tests of the StoPoren Panel Facade system to demonstrate compliance with the relevant performance requirements of the NZBC. STO have experience working with facade and fire engineers on buildings that fall outside the scope of E2AS1, and our facade and render systems have a proven performance history both in New Zealand and overseas. STO facade systems incorporating the STO RMAT render system are covered by a 20-year STO RMAT warranty with STO service assurance. Just a couple of reference projects. Frame Apartments in Wellington completed 2018, Archouse Architects, 18 stories, approximately 60 metres high, clad with a combination of the StoPoren Panel Facade system and our StoTherm masonry insulation system. It's a fantastic example of what can be achieved with a render finish. Retirement complexes, another big market for us. The Orchards by MetLife Care in Auckland, Arcline Architecture, is a good example of what is happening in the retirement complex space. Buildings are getting bigger, they're getting taller as we look to increase density. And Preston Residences in Christchurch, another StoPoren job, a really good example of higher density housing. Rockwell Group Context Architects, a really nice example. Thank you very much. Happy to take questions, Matt.
Great, thanks, Jason. I will, let's just bring you back on screen. Hey, now, what I thought we would do, I've got a couple of questions I'd like to go through. If anyone's got any comments, then they can put them through on the chat line. But I was just going to put a poll up there and to get some feedback. Here we go. So just the question is, what's the main consideration for you when you're specifying a facade system? And just the consideration of what Jason has been talking about. So Jason, I'm actually just thinking about your experience with facade engineers and what sort of documentation they're looking for, when they're specifying your system. Obviously, you guys have got some test data and you've got your data sheets. Mm-hmm. If you find that typically is all that's required in terms of meeting compliance requirements, or is further sort of specific design engineering required?
Yeah, that's a good question, Matt. A lot of the information that we're able to provide, and particularly the AS/NZS 4284 facade test, seems to be the starter for 10 for most facade engineers when they're looking at specification.
Yep.
That covers weather tightness well. It also helps assess the structural performance of the facade. But in saying that, also the work that we have had done as part of our StoPoren appraisal, although the appraisal scope is, if you like, defined around E2AS1 type buildings, there's a lot of information in that appraisal that is relevant for buildings outside of that scope as well. Now we obviously have that information available, and I think probably fire is a good example there. that is taken and used. So look, we've had some very good success on a number of our multi-story facade projects, working in with the fire and the facade engineers.
Yep.
Obviously, facade engineers, if they do want to vary part of the system, as is their right, that is absolutely fine too, and we're happy to work with them on that basis.
Got it. We're asking about main considerations for a facade system when thinking about specifying, and one of the questions is around maintenance. So tell us about the maintenance requirements for your systems.
Yeah, look, sure. About 3 years ago, Sto introduced the Sto Service Assurance Program. We introduced that really to assist building owners with their maintenance obligations. What that involves is every 2.5 years after sort of practical completion, if you like, the building owner is contacted. They're put in touch with the Sto contractor, and the Sto contractor will actually come back and carry out an inspection of the work that was carried out. The main driver behind us doing that was to ensure that every sort of 2.5 years the building is getting a good maintenance inspection, and it just gives us the ability to pick up on small issues that may be occurring while they are small issues, rather than waiting 10 to 15 years at the time of a repaint and find that there's some more significant work that needs to be done. A good example of it is Ryman Healthcare and their villages. We do a lot of work in that space. They have instigated a maintenance program based around sort of Sto service assurance in some ways, and that has actually given them the ability to actually sort of stretch recoat periods where we may be typically looking at a 10-year recoat period for the paint system, to actually push that out into that 13-year space plus, just through having a really good maintenance program in place.
Got it. Wow. Look, I thank you for that. I just going to finish up the poll and publish those results now. So got them on everyone's screen. Can you see that, Jason?
I can. That's great.
Yep.
Yeah.
Great. So we've got aesthetics, the largest consideration, followed by cost, and then compliance and maintenance. Okay. So any comments there?
No, look, I think from a render facade perspective, aesthetics is a big thing for us as well. Obviously, with quite a range of finishes now, it is not just the render isn't just a stippled render finish anymore. As you saw with the frame apartments building, there are ways of introducing a lot of variety in a facade using a render system. So that sounds good to hear.
You touched briefly on the current, I suppose, discussions and suggestions around changes to Clause C in terms of fire. So you, and the fact that we might actually be bringing in an additional category, you suspect. Any other kind of lead kind of changes that you can see coming?
Not specifically. I think what we are certainly seeing from a query perspective is around more that entire system approach. It's no longer just sufficient really to hand across a cone test report that says you've got a performance level A from a fire spread perspective. It is a full system approach. It's looking at everything from the wall underlay with rigid underlay out. I think as soon as some of these international tests are referenced within the building code, there will be possibly more of a drive to be able to demonstrate compliance with those.
Right.
And that's probably a part 2 seminar at some stage for you, Matt.
Okay, well, we look forward to that. And on that note, why don't we conclude? We'll bring you back after Philip's presentation, but I will take over the screen, and Jason, we'll see you a little bit later on.
Thank you.